When dealing with stoichiometry, we've learned that you can use the moles in the balanced equation to convert from the moles of one thing to the moles of something else, simply by using those coefficients in the balanced equation. One of the things we can also look at, though, is we can look at actual chemical formulas. For example, carbon dioxide. Let's say we have 1 mole of CO2. If we have 1 mole of CO2, is it fair to say that in 1 mole of CO2, we really have 1 mole of carbon atoms? Because if we have a mole of CO2, again, what does that mean? It means we have 6.02 times 10 to the 23rd CO2 molecules, okay? And of course, if we have 6.02 times 10 to the 23rd molecules of CO2, of course, we have 6.02 carbon atoms because every CO2 molecule has 1 carbon atom in it. And hopefully you can also see that since it's CO2, 1 mole of CO2 absolutely contains a mole of carbon atoms. We can also say it contains 2 moles of oxygen atoms. And so we can use this relationship just like 3 moles of CO2 makes 8 moles of C3H8 or something like that. We can use that logic just like we do with the balanced equation. We can say that 1 mole of CO2 equals 1 mole of carbon atoms, or 1 mole of CO2 equals 2 moles of oxygen atoms, just like we did with when we use balanced equations to do stoichiometry. Okay, and that idea leads us to what's called combustion analysis. And combustion analysis is basically a process by which you can take a chemical compound and you can burn it. And when you burn it and you figure out how much product you get, you can use that product to figure out what the unknown compound was that you started with. So you have some unknown compound, you burn it, and then you look at the products, and you can use the amount of the products to figure out what that unknown compound was. So when you burn something, typically you burn something. Anytime you burn something, it's reacting with oxygen in the air. And typically, the 2 products you most typically get are carbon dioxide and water. Obviously, when you burn something, it releases a lot of heat, but heat is not a chemical, so you don't see the heat in the chemical reaction. So basically what we're going to do is we're going to analyze the CO2 and the H2O part, and that's going to help us figure out what this original compound was. Okay, so here are the steps to do that. You can look that over yourself. I'm just going to jump right to the example. The first example, I try to show everything here for you. But again, look over steps 1, 2, 3, and 4 here, and that will hopefully get us to where we need to be. We are basically combining stoichiometry with, remember the airplane assignment about who blew up the plane, the percent to mass, mass to moles, divide by small times to whole. We're combining those 2 things basically together here. So in example 1, it says 8.410 grams of an unknown hydrocarbon. That might be a new term for you. Hydrocarbon is exactly what you think it is. It's something that has hydrogen in it, and it's something that has carbon in it. And it only contains those 2 elements, hydrogen and carbon. So a hydrocarbon is just like CH4 or C3H8 or C5H12 or there's thousands of different hydrocarbons. Okay, but those are just a few examples of hydrocarbons. So this hydrocarbon completely combusts an oxygen gas. It makes 25.23 grams of CO2, 13.76 grams of H2O. And they want us to determine the empirical formula of the unknown hydrocarbon. So we're trying to figure out what compound is this. So step number 1 above says convert grams of CO2 to grams of carbon. So I'm going to take my 25.23 grams of CO2, and again, anytime I have grams, the only thing I can do is convert to moles. And so the molar mass of CO2 is 44. And then here's the part where I talked about earlier. Okay, 1 molecule of CO2 contains 1 atom of carbon. So we can say that a mole of CO2 contains a mole of carbon. So that's now my kind of like my stoichiometry step there, where I'm going from the whole molecule to just one of the atoms in the molecule. Okay, and then I can say 1 mole of carbon has a mass of 12 grams. Again, that's the molar mass of carbon. carbon, and then this one here obviously is the molar mass of CO2. So that means that 25.23 grams of CO2 contains 6.881 grams of carbon. Okay, now step number 2 is we have to do the same thing with water. Okay, notice step number 2, convert grams of water to just grams of hydrogen. So we're going to take the 13.76, which we had up here. We're going to take those 13.76 grams. There's 18 grams in 1 mole of water using the molar mass of water. Okay, and then this step right here, this is, if you're going to mess up, this is where students mess up. Because 1 mole of water does not contain 1 mole of hydrogen. Look at that, there's 2 hydrogens. So for every 1 molecule, there are 2 hydrogen atoms. So 1 mole of water contains 2 moles of H. And then here, 1 mole of H has a mass of 1 gram. Okay, and then I got 1.529 grams of hydrogen. Okay, now, I'll tell you right now, anytime you do a combustion analysis problem, these first 2 steps will always be exactly the same. You're going to be starting with a different number here and here, but the process is exactly the same every single time. You're going to end up with grams of carbon and grams of hydrogen every single time. Okay, now we need to make sure, and now in this problem we know, but we need to make sure there's not something else in this compound. For example, this unknown compound might be like C3H8O. But we know it's not because it says hydrocarbon. So basically what you want to do is you've got this number right here. So you want to take that mass that you started with and then subtract the carbon and subtract the hydrogen. If it equals 0, then you're good. Then that means that there are no other elements in there. Okay, what if it didn't come out to be 0? Then it's very likely that you have another element in there, and usually it's oxygen. Okay, and the reason that we know that it's oxygen is because look at your products. You only have carbon, hydrogen, and oxygen in the products. Now, the oxygen that's here and here might have all come from that oxygen right there. But if not, where would it had to have come from? It had to have come from this compound. In the next example, we'll see one like this where it doesn't equal 0. In this case, we subtracted the carbon, we subtracted the hydrogen from our initial mass, and it does equal 0. And the fact that they told us at the beginning of the problem that it's a hydrocarbon, we know that it has to be only carbon and hydrogen. So in this case, there's no mass that's unaccounted for, so we know there's no oxygen in this compound. Okay, now our last step is to do what we've done in the past, percent to mass, which is already done, mass to moles, which is here, and then divide by small, and then times till whole. So we did get 1 carbon and 2.67 hydrogens after we divided by our smallest number. So 2.67 means we have to multiply by 3, and so we end up with a final formula of C3H8. Okay, so notice that the one step that we didn't do there was the percent to mass. Okay, the percent to mass one, these are already masses. We've already got those in grams, so we don't need to do that first step. So we just did the mass to moles, divide by small, and then times till whole step. Okay, and then just like always, if they say the empirical formula is this, and then they say, oh, by the way, the molecular formula has a mass of, let's say, 132 grams per mole. What is the molecular formula? Remember that to do that, you have to get the molar mass of this, which is 44, and you take 132 divided by 44, that equals 3, and that means you would multiply everything in that formula by 3. Okay, and that one would be the molecular formula. Okay, let's look at another example where it's not done for us. Okay, and you can see right away the molecular formula part is there. So 1.97 grams of an unknown compound completely combusts, produces 3.94 grams of carbon dioxide and 1.61 grams of water. Now it doesn't say hydrocarbon in this case, so there might be another element in there other than just carbon and hydrogen. Let's see. So our first step, we're going to take 3.94 grams of CO2. There's 44 grams. And again, if you look at the example above, this after this number right here, everything else looks exactly the same. in 1 mole of CO2, there's 1 mole of carbon. And in 1 mole of carbon, there are 12 grams. So now I go to my calculator. I take 3.94. I divide by 44. I multiply by 12. And I get 1.07 grams of carbon. Okay? And then I'm going to do the same thing with water, 1.61 grams of H2O. There are 18 grams in 1 mole of water. And then again, in 1 mole of water, there are 2 moles of hydrogen. And then 1 mole of hydrogen has a mass of 1 gram. So I'm going to take 1.61, I'm going to divide by 18, and I'm going to multiply by 2. And I get 0.18 grams of hydrogen. Okay, and now I need to make sure, is there anything else in this compound? So I'm going to take 1.97, I'm going to subtract the carbon, I'm going to subtract the hydrogen. 1.97 minus 1.07 minus 0.18 equals 0.72. So there is, and again, it says it only produces carbon dioxide and water, CO2 and H2O. We've already accounted for the carbon and the hydrogen, so that 0.72 grams has to be oxygen. Okay? So now we're done with that part. We've got our mass of carbon, our mass of hydrogen, and our mass of oxygen. Those three do add up to the 1.97 grams. So now we do the percent to mass, skip that part, mass to moles. So 1.07 grams of carbon, 12 grams in 1 mole, 0.18 grams of hydrogen, 1 gram in 1 mole. Hydrogen's always easy because it's always the same number. And 0.72 grams of oxygen. And oxygen has a molar mass of 16 grams per mole. So 1.07 divided by 12 equals 0.089 moles of carbon, and 0.72 divided by 16 equals 0.045 moles of oxygen. So our smallest value is clearly 0.045, so we're going to divide everything by 0.045. Okay, and so we end up with 2 moles of carbon. Again, very, very close to that. We can round that to 2. Okay, 0.18 divided by 0.045 equals 4 moles of hydrogen, and oxygen is divided by itself equals 1 mole of oxygen. So our empirical formula is C2. We don't have to multiply to get to a whole number, right? So it's C2H4O is our empirical formula. Okay, and then part B says the molecular formula has a molar mass of 88. What is the molecular formula? So let's add this one up. What's the mass of C2H4O? 24, 28 plus 16. So this one has a molar mass of 44. The molecular formula has a mass of 88. So if this one's 44, 88 divided by 44 equals 2, which means we have to double everything. So that's going to be C4H8O2, and that is our molecular formula. Okay? And that is how combustion analysis works. And if you look at that, man, that's a lot of work. Okay? But again, this is stuff you've already done. This is really our new part right here when we're using the chemical formulas to go from the whole formula to just one of the atoms in the chemical formula. The rest of this is all just kind of combining stuff we've already learned